In this video, I'm going to explain how to construct a confidence interval for the difference between two means when you have matched paired samples. The assumptions for the procedure are that you have two samples, but they're matched paired together, and that each sample is large with 30 or more data points, or you know that each sample comes from a population that is approximately normal. We're going to have a little bit of new notation. D bar is going to be the sample mean for the differences. So we're going to compute a third data set, which will be the difference set. And for that data set, we'll find its sample mean, we'll find its sample standard deviation, and then we'll be looking at a confidence interval for the difference, the mean difference of the two populations. The procedures for constructing the confidence interval are going to be exactly like constructing a confidence interval for one population using the student's t distribution. Let's look at this example. Brake wear. For a sample of 9 automobiles, the mileage in thousands of miles at which the original front brake pads were worn to 10% of their original thickness was measured, as was the mileage at which the original rear brake pads were worn to 10% of their original thickness. The results were as follows. Construct a 99% confidence interval for the difference in mean lifetime between the front and rear brake pads. And then we have a part B that we will do after we do part A. So we're given this data set of 9 data points, which is small. So we would want to assess normality. We could probably assume from just life experience that the wear on brake pads is normally distributed. But just in case it's not, we can look at the data sets. I've got the data sets in technology, they're in Desmos, and I'm using the table feature, and I've rewritten the headers R for rear brake pads and F for front brake pads. So at this point, I will create dot plots for both. Especially, I'm picking dot plot because the data is so small. And let's look at this. Let's do exact and let's change the width to, and we can see the data. What we're looking for is any strong skewness, any strong sense of outliers. Don't really see any with the first data set. Let's look at the second data set, hiding the first. And again, we don't see any strong outliers. Here are the two data sets graphed together. You can see the difference in the range of the data. The orange data set representing the front brake pads seem to have a lower life in terms of mileage versus the rear brake pads. Something that, if you know anything about cars, probably these vehicles are all front wheel drive. So that is impacting the brake wear. Nevertheless, they both look like they are coming from populations that are approximately normal. So we will proceed with the procedures. I need to compute the difference data set. And this is the nice part with the technology. We're going to compute the difference, and that's going to be a third data set. So over here in this column, I'm going to do R minus F. And here is the data set for R minus F. Given this data set, I will find its sample mean and its sample standard deviation. Let's see, the mean, I will round to 2 decimal places, so 10.26. And the standard deviation, again, we'll round to 2 decimal places. The degrees of freedom are 8, and we're going to pull up the student t distribution now. I'm computing a 99% confidence interval. That means alpha, which is the outer, will equal 0.01. And here are the critical values I get for this symmetric distribution. Now I'm going to calculate the standard error and then the margin of error. The sample standard deviation was 9,200 divided by square root of the sample size, which is 9. That's the standard error. And then the margin of error is the critical value times the standard error. The confidence interval is going to be the 10.26 And if we label the margin of error M, we can compute 10.26 minus M and 10.26 plus M. Be aware if you need to translate your answer into the 1,000-mile unit, and you would do that by multiplying all of your values by 1,000. That will move the decimal place 3 places to the right. So for example, we're pretty much saying that the difference in the where is about 10,000 miles. It ranges from 9,230 miles to 11,290 miles in our 99% confidence interval. Now let's go answer part B. Part B says, an automotive engineer claims that the mean lifetime for rear brake pads is more than 10,000 miles more than the mean lifetime for front brake pads. Does the confidence interval contradict this claim? So the lifetime for rear brake pads is more than 10,000 miles more than the lifetime for front brake pads. Well, in our calculation, we did R minus F. So if the rear is more, the values are going to be positive, and that's what we see here, right? We see the rear minus the front equals mostly positive numbers. In every paired data set, the rear brake pad had a longer lifespan. And so when we look at our confidence interval, we see that the 10,000 that he's asking about is in. So the confidence interval supports. Now he says more than 10,000 miles. But again, if we look at this from a number line perspective, it doesn't always have to be more than, because here's the 9,230. Here is the, let's say, 11,290. Let's say that 10,000 is somewhere here. Well, while the whole band can be within there, there's a space where just to the left of 10,000 where we could fall, and in that case, it would not be more than 10,000. So in terms of the claim, it's a pretty strong claim because there's a possibility that we could be less than 10,000. So I would say that, it doesn't contradict it, but it doesn't wholly support it. If he said over 9,000 more, then absolutely. Him saying over 10,000 more, not always. There's a span of space here where we could have samples that fall here, and then they would be less than the 10,000. So I would say that the claim is not fully accurate. It's a little too strong, and that's what the data is showing us. This is how you compute the confidence interval for a matched pair. And in essence, you see that after computing the difference set, the process is just like computing a confidence interval for a one population mean standard deviation unknown.